that. Now let's deal with Ernie up here. Forget Bert momentarily. So we've reached a bit of an impasse. And the impasse so far is that if we simply look at the distance from average, and I like using the negative. I like using the negative values because that tells us it was below average. If we just say it's 2 away from average, that means that it's 2 up or 2 down. So we're going to lose how 2 it is. How 2? Ooh, that's a strange sentence. How 2 is it? It's 2, up, down. So the idea is we need to do something to these numbers to control. Because right now the problem is if we sum up those differences, it always sums to 0. That's a problem. That's a problem. You can't sum them. Well, you can sum them, but it's always going to be 0 based on what Aaron said about balance. So that doesn't help us a whole lot. Because that means any data set, no matter how inconsistent or consistent, is going to sum to the same thing, which makes it seem like every data set has the same variability, which is ridiculous. Because you've already agreed in your guts that Bert is less consistent than Ernie, but we haven't measured it correctly yet. So what do we do with these numbers? Cody's vote of absolute value is not used. So here's what is used, and it might not make sense, but here's why.
Well, my actual vote is squaring them.
That's right.
That's what
oh, Cody proposed square. Good. One way to get rid of this cancellation problem is to square the results. That will get rid of the negatives, won't it? It'll take a 0, make it 0. It'll take the 2 and make it 4. It'll take the 1 and make it 1. It'll take the negative 2 and make it 4. It'll take the negative 1 and make it 1. That's one way of getting rid of the negatives. Anybody confused as to why you would square? I was. When my prof first told me this, I went with Cody's. I'm like, take the absolute value. Seems the most logical. He's like, yes, but, was that Dr. Taylor? Was there Dr. Taylor, Dr. Larisha? I forget which one. I was the thorn in, or Dr. Mason. I had 3 of them. I was a thorn in their side. Why? So I always encourage you guys to ask why. I was that kid. Why? I don't get it. Why? After class, why? Here's why. They never told me. The answer I always got was because it's just the way it is. I'm like, that's why I couldn't stand my mother when I was 16 years old. Because, why? Here's why. I'm going to show you why. I love my mom. Mom, I love you. Here's why. And it's okay if you don't remember this. In 105, we didn't attack this at all. We attacked parabolas a little bit in 105. But we didn't talk about absolute value at all in 105. So Cody, at heart, there's a difference in the graph of an absolute value function versus a parabola. If you square something in mathematics, it becomes parabolic. If you take the absolute value, it's a V-shaped graph. So an absolute value curve generally looks like that. It's got a sharp point at its base or its vertex. Whereas a parabolic curve has a smooth V shape. So absolute value has a sharp pointed V, whereas a parabola has a smooth rounded V. Now, mathematically, who cares? Well, if you study what's called calculus, which is what quite a bit of statistics is based in, you have to care. Because very often, well, let me give you a theoretical. If you had a choice between low variation and high variation, what would you rather in your lives? So consistency or inconsistency, what would you choose? You would probably choose consistency. So for example, you're manufacturing bolts and nuts, or you're manufacturing climbing holes, or you're manufacturing skis with the edges on the side, or you're manufacturing anything, food products. You probably don't want inconsistency. I got a 16-ounce bag of chips. Might be as low as 2 ounces, might be as high as 5 pounds. You're not going to be able to sell that, okay? You don't want, that's a ridiculous example, right? So what you want to do is have as small a variance as possible. What would be the ideal variance? Ideal would be none, correct? They'd all be exactly the same, which doesn't happen. But that's ideal. What calculus, the entire branch of calculus does, is it tries to minimize or maximize, depending on what you want to do. It optimizes. You cannot optimize this curve. Curves that have points in them like this cannot be optimized. Curves like this that actually don't have points, that are smooth and continuous, can be optimized. That is what I finally discovered is why we enjoy it. That's one reason. That's the most logical reason. There's also a more mathematical reason on the enrichment page if you want to see it, which I don't encourage you to go to, because it'll probably just make you vomit. But that's the logical reason. You can't optimize an absolute value, but you can optimize the parabola. Okay? You don't have to worry about it. Once we do it once by hand, you'll never do it by hand again. The important thing is these two have similar shapes, yes? Similar shapes, which means the number we get out of this one is going to approach what Cody's number is, which means you can think of it the same way. It's an average distance from the average. But just realize the computation, we'll come back to that, don't worry, we're going to come back to that. We're going to have you say that over and over and over again. Yeah, but we have to, because that's the whole point. So, Cody, thank you for that. Friends, just realize that although Cody's is way more commonsensical, it's not what's used because of that, So now we have what's called the squared deviations from mean. So each data point, squared deviations from mean. The problem, of course, is that that unit really doesn't make any sense. Let's add it up, shall we? Let's add these up. Sum up the squared deviations from mean. That's attached. What do you get? 10. 10 what? 10 points. Careful, one more word. 10 points squared. That's 10 squared points, isn't it? Because remember, these were all points. 0 points, 2 points, 1 point, -2 point, -1 points. Then you squared them, and it became 4 squared points. 2 or 1 squared point, 0 squared points. So right now, this is 10, and if you want a unit, it's 10 squared points, which is meaningless. Doesn't mean anything. So at some point, we've got to get that back. And how do you think we're going to get rid of points squared and make it just points? We're going to take a square root to clear it out. Right, but not yet, not yet, not yet. Because that, by itself, is kind of misleading. What did Cody do? What did we all do, actually? We kind of did it together. Once we had those individual distances, the 2, the 1, the 0, the 1, the 2, what did we do with those? We added them all up, right? To get 6, and then we took the average of them. Yes, we took the average. Let's do that one more time for this. Let's average that, correct? So that's the whole idea, is on average, how much is the consistency varying? So, the one thing, and this is the part that has no good logical explanation. Let me go. Can I dump this? Is that okay?
Yes.
Is okay? Okay. So we're measuring Ernie's consistency continued. Notice if you divide that by 5, you're going to get 2. That makes sense? 2 squared points. Now, this is Ernie continued. When you take the sum of the squared deviations, we get 10. Now, logic would say divide it by 5. But you don't actually divide it by 5, you divide it by 1 less than 5. It's a purely mathematical reason, don't worry about it. If you want to know why, I've got it on that enrichment page of the website. I've got a very nice mathematical proof for you if you want to understand why. It's there waiting for you. If you ever have trouble falling asleep at night, that'll put you right out. So what you do is, you actually take this value and you divide by 1 less than the number of data points you have. There's a very good mathematical reason. Like I said, everyone's like, I don't buy it. I didn't buy it either. Dr. Mason, why? Why? That was me.
Degrees of freedom.
That's the correct statistical reason. It's called degrees of freedom. If you want a mathematical plus terminological one, check out the solution I've got. I don't want to. I've tried to do it in class before. It loses everybody. So I stopped. Because this is the only time you'll ever calculate it by hand anyway. But it is n-1 degrees of freedom. But numerically, all that means is you take 10 square points, right, square points, and divide it by 4. Because you have 5, divide by 4. So now you have 2.5 squared points. What that is called, right there, that number is called the sample variance. This actually has a name in statistics. It's called the sample variance. It is used for some statistical studies. Not many. Not many because of the unit, points squared. That's kind of dumb. Square point. I don't know what a square point is. I can't envision what a square point is. But It does have a special symbol because it does get used quite a bit. It's called little s squared. Little s. And little s is a nice one. Sample variance. Say that again?
Can you just put the little s?
Oh yeah, we'll put it in both places in a second. I want to add it to Bert and Ernie's. Because s squared isn't as important, Michaela, as the square root of it, which you guys voted for earlier. Remember you said, we got to get rid of that squared points crap. We got to get rid of that squared points crap. We have to get it down to a single sensible unit. And that's what you do next. You actually take the square root of all of this. This. Now, look at how awful this looks, friends. Look at that. Terrible, yes? Terrible. Most of the time when I talk to students that have had a statistics class, they cringe. Some of them vomit. And they say, oh my God, that course was nothing more than formulas. And I told you guys, there are only 2 formulas you'll use repeatedly in this class. This is not one of them. This is the only time we'll use this formula in this class, is right now. So what you're going to do is, you take the square root of 2.5 points squared. And you end up with what? Well, what's the square root of 2.5 though? 1.5? No, more than 1.5. 1.6? 1.6? 1.6 points. Boom. 1.6 points. That is close enough to the 1.2 we got before. On average, it's actually a better estimate. I'll come back to that in a second. But that right there, that guy, see, he's the square root of s squared, yes? Which makes him just s. That makes him just s. He is the most important measure of variation we will use in this class. He's called the sample standard deviation. Sample, let's come back on the front board. Michaela, yes, I like your idea. I want to come back here. Go ahead, Zach.
Isn't it when you have something squared and then square root and the square root and the square cancel each other out?
Exactly, but you have to also take the number into account too. The square root of 2.5. 2.5 is under the radical as well. What's the square root of 2.5? About 1.6. So yes, you have to, if you will, apply the root to every factor underneath. That's why the point squared goes to just points. But the 2.5 has to be brought down to his square root as well. Is that fair? Yeah. That makes sense to you? Fair enough. So what I want to do now is, I want you guys to forget this. It's in your notes, I know. Don't cross it out of your notes. But the torture of calculating that manually, I could see the lack of interest creeping in. The further we went down to that calculation, and by the time I put that last square up, I'll look around and I could just see tears. That was awful. It is awful. Imagine doing it on a sample size of 100. Get it. Good. Don't imagine, because you're not going to. You're not going to ever again. That's the one and only time you're going to calculate it. But why did I make you do it once? Why did I make you do it once? What's the point?
Appreciate the $100 calculator.
Well, not even that. That's kind of that's a reason. I like it's a good one though. It's a little defeatist. Because if I just was to tell you, okay, so here we go. We're back to Ernie, more consistent. So let's measure variability. Variability, okay? Ernie's, he has an X bar of 81, an average of 81, and he's got a sample standard deviation of 1.6. These are both points. You now have an idea of what 1.6 points means. What does it mean? 1.6. What is it? What is 1.6? Please, Chili!
Average distance from the mean.
Did you hear what she just said? It's the average distance from the mean. If you figure out how far apart each of those test scores are from the mean, it's about 1.6 points. So now you have the average above it, 81, and you also have this idea of how far away on average are the test scores from that. Well, about 1.6 points. Is any one of them 1.6 points away from average? No! That's because an average doesn't have to be one of the data points. The points were 2, 1, 0, 1, and 2. The way this averages it is closest to 1.6. Now, you might say, wait a minute, time out, damn it, rule? Cody's way, it was 1.2. Correct. But this computation does a better job of approximating the population than Cody's does. I mean, it has to do with the mathematics of the parabola versus the absolute value. Don't worry about that. Don't care about that. I don't want you to care about that. What I want you to focus on is the interpretation of what the 1.6 means. So here's a question for you guys. What's Bert's? What's Bert? We know his average is 81 points. What's his standard deviation? What do you think? Guess first. Guess right now. How many points? More or less than 1.6?
More.
Probably more. Give me a number.
20.
20. 20 it is! There's our one vote. Everybody's asleep. I'm done with this crap. Okay, we're done with this crap. We're not going to calculate them by hand anymore. Grab your TIs. Grab your machines. This is how we do it from now on. We'll come back to this. Now, I don't have an overhead in here, so I'm going to throw the TI up on the screen. Yeah, that is tedious. Oh, there is! Thank you. I didn't see that under there hiding. Excellent. That makes it very, very much nicer and right on this graph. I wouldn't even seen that, Zach. Thank you. All right, let's plug you in. Do you work? Yes. In there. Let's get you in focus. All right. Beautiful. Now, if you have other technology, totally fine. If you have other technology, it's totally fine. If you want to use other technology, it just might not look or behave the same way as the 83, 84 does.